Don't disturb. I'm very busy with work. What? I need to make a video on work today? Alright, let's get started then. Hi friends. In this video, we'll be doing the physics definition of work, the formulas to calculate work done, and then we'll do our top 3 test-oriented questions on this topic. I'm sure by the end of this video, the concept of work will be really clear to you. Now, what comes to your mind when you hear the word work? Are you thinking about your homework or the work of cleaning up your room? For me, my work today is to make this video for you. The physics definition of work is very different from our everyday use of the term work. In physics, work is done when there is a force and there is a displacement involved. The formula to calculate work done is force into displacement in the direction of the force. To understand this, let's do a simple experiment together. For that, I need you to get an object like a book. So pause the video right here and go and get a book. So are you ready with your book? I'm ready with mine. Otherwise, pause the video here and go and get a book. Now, when you hold the book like this, are you doing any work right now? The answer is no, because there's no displacement of the book. But if you go ahead and lift up the book like this, have you done any work? Now the answer is yes, because there is a force involved and there is a displacement. So you can feel the force when you're lifting the book, and this is your displacement of the book. So let's say in my case, the force is about 10 Newton. And the displacement from here to here is 40 centimeters. So how much work have I done? Let's use the formula work equal to force into displacement. So that's 10 Newton into 40 centimeters. Now I need to convert that to SI unit. So it's 0.4 meter. So I get 10 Newton into 0.4 meter, which is 4 Newton meter. And we know that Newton meter is basically joule, which is the SI unit of work. So I've done 4 joules of work right here. Let's put this important formula of work done on our concept board. Let's also place the SI unit of work done, which is joules. I stole my daughter's toy for this demo. So if I pull the toy like this, I'm doing work. As you can see, force and displacement are in the same direction here. Now an interesting question is it possible that force and displacement are not in the same direction? What do you think? The answer is yes. Let me show you. So suppose if I now pull the toy like this, as you can see, my force is along the string, but the displacement is along the table. So there's an angle between the force and the displacement here. Now, how do we calculate the work done for this case? So let's zoom in and see. So as we saw here, force is along the string and the displacement of the toy is along the table here. To make it easy, rather than finding the displacement in the direction of the force, we are going to find the force in the direction of the displacement. So for that, I want you to consider this right angle triangle here, where here's the right angle and here's the angle theta between the force and the displacement. So as you can see, the force is along the hypotenuse of the triangle. But we are interested in finding the force along the displacement or along the base of this right angle triangle. So what will be the component of the force along the base? That's right, it's going to be F into cos theta. So what will be the work done here? It's going to be F cos theta into the displacement. So if I rearrange that, I'm going to get W equal to Fs cos theta, where theta is the angle between the force and the displacement. Let's put this formula onto our concept board. This first formula works only when force and displacement are in the same direction. The second formula, W equal to Fs cos theta, is more powerful and works for any angle between the force and the displacement. Let's look at 3 cases where we can apply this second formula. Case 1. So when I push this block along the table like this, as you can see that the force and displacement are along the same direction. So what is the angle between the force and the displacement here? That's right, it's 0 degrees. So if we use our general formula, our work done will be W equal to Fs cos theta. And we know that the angle theta is 0 here and cos 0 is 1. So we get W equal to F into S, which is basically the first formula that we did in this video. Case 2. Suppose a person is walking carrying a bag as shown in the picture here. So to find the work done, we need to look at the force and the displacement here. So what is the direction of the force? So since he is holding the bag, the force is in the vertically upward direction. And the displacement is along the path he is traveling. Now, what is the angle between the force and the displacement here? That's right, the angle is 90 degrees. So now let's use our formula W equal to Fs cos theta. And we know that cos 90 is 0. So the work done actually turns out to be 0 in this case. Now, how is that possible? Is there any other force for which he is doing non-zero work? The answer is yes. It's the force of friction. So when he's walking along the path, he's doing non-zero work against the force of friction. So an important exam tip is that to find the work done, you need to carefully consider the force involved and the displacement. Case 3. If I lift the book like this, what is the work done by the force of gravity here? So last time we looked at what is the work done by us. But now we are interested in the work done by the force of gravity. So what is the direction of the force of gravity? That's right, it's vertically downwards since it's the weight of the book. But what was the direction of the displacement here? As you saw, it's vertically upwards. So the force of gravity and the displacement here are in opposite directions. So what is the angle between the force and the displacement? It's not 0 degrees, it's going to be 180 degrees here. So now let's use our formula W equal to Fs cos theta. And we know that cos of 180 is minus 1. So the work done in this case turns out to be negative, since force and displacement are in opposite directions. So we've learned that work done can be both positive and negative. So let's put all these 3 cases onto our concept board. So this is the concept board that we've built along in this video. I would encourage you to pause here and take down notes. Now that we have finished the concept of work and the formulas to calculate work done, let's move on to our top 3 exam-oriented questions on this topic. Here are the top 3 questions.
I encourage you to pause here and try to solve these questions. I'll be posting a video on the solutions soon. You can find a link to the solutions video in the description below or search for it on my channel page.
So I hope the concept of work is super clear to you now. And do remember that the physics work is very different from our everyday use of the term work. In this video, we've learned that work done is force into displacement. There's a second formula to calculate the work done, which is change in energy, or to be more specific, change in kinetic energy. So if you want to learn more about that, you can watch my video on energy. I'll be putting a link in the description below. And I have a little work for you at the end of this video, which is to like, comment, and share this video, and also subscribe to my channel. Thanks for watching.